Well, good morning and good afternoon, everybody. This is Mr. Kinney. We're going to be doing notes today on acid-base titration. And this is a great time for us to do this because we've just learned about solutions and calculating concentrations and how to dilute them. And we're beginning acids and bases. And a lot of times in chemistry, to figure out how much of a chemical is present, you'll do a titration reaction. And it can be a lot of fun. And we'll get started with this. So I'm really looking forward to this. I hope you'll enjoy it. Let's get this camera zoomed out. And then for my substitute teacher today, at various times students are going to need to, you can pause this by pushing the enter button on the top of the doc cam, and that'll pause it. Don't hit the freeze stop button, or you'll have to restart the whole thing. So to begin with, so here's the definition. Let me read it first, then we can pause this. Okay, so it's a lab procedure. Oh, let me get it so we can see the whole thing. It's a lab procedure to determine the unknown concentration of an acid or a base. And base is known as the concentration, a base of known concentration. So we're going to know how much what the molarity is of the base, probably 0.1 molar, and we're going to slowly add it to an acid of a molarity that we don't know, until they completely neutralize each other. And we'll have a chemical indicator that'll change a color for that. So at this point, this would be a good time to have to hit the enter button and pause so students have time to get this written down. So here's some terms that you're going to need to know for working with this. First of all, we'll be working with a standardized solution, and this will be an acid or a base that we know precisely what the molar concentration is. Usually we'll be using 0.1 molar, probably sodium hydroxide, which is a base. You should know by now, we see that OH, that means there's a base present. And then we got sodium ion. And I'm going to go ahead and do that. We can pause this and then students can get these written out. I want to talk you through each of these. We're going to add a chemical indicator, and that's going to be a natural dye that'll change color in the presence of an acid or a base. We'll be using one called phenolphthalein, which, oh, there's our warning bell here. We'll be using a chemical called phenolphthalein, which will turn a pretty pink color in the presence of a base. And so when we start working with our acids, it'll be clear. Then as we start adding more base in, and we'll add it with a device called a pipette. Here is just the bottom part of it. It's got a valve here that we can turn and let fluid through. There's numbers on here that let us know precisely how much we put in, and we're going to be able to figure out how much volume of a particular chemical. Oh, I'm getting ahead of myself, sorry. So we're talking about the indicator. So this one will be phenolphthalein. Now look, don't be writing all the stuff down right now. Let me talk you through it, and then we'll pause it through there. The equivalence point. So this is when you have just enough base has been added to an acid to form a neutral solution. Because the basic equation we've got when we do these is that we're going to take hydrogen, which is an acid, I'll call that HA. Don't write this down, please listen. We're going to add it to a base, which we will call B for base with OH. And those two will react, and what they're going to form is water plus, you're going to get, I'm going to call it compound AB. A and B are both going to be some type of a metal. This will end up being called a salt, a metal bonded to a nonmetal. Yeah, this will be a metal that'll probably, usually bases are nonmetals on there. I might have said that backwards. I think usually bases tend to be metals, and then the acids tend to have a hydrogen on it, which typically is a nonmetal. Anyway, the base equation is we add these together and we get water and we get a salt, and this neutralizes. And then the last thing, before you start furiously writing all these down, is the end point. And this is going to be the point when the indicator, in this case the phenolphthalein, when it finally changes to the beginnings of a slight pink color. And that's going to indicate at that point you have reached the point where where the base that you're adding has completely neutralized the acid, and you stop right there, you record the volume on your burette, and then we can do calculations to figure out how much of the acid was there. So at this point, this would be a good time to pause this. Let me see if we can zoom it in a little bit more so you can get these. Okay, that was too much. All right, so if I could have my substitute, please push the enter button to pause this until students feel like they're ready to go on. All right, everybody. Titration calculations. So let's get this going here. So in a titration, the equivalence point is reached when the moles of the hydrogen ion, the acid, equal the moles of the hydroxide ion, which is the base. And that's the point, at least in this one, when we go from a clear solution, and you'll be swirling this in a flask, and as you add drops of the base to it, you're going to slowly see momentarily it'll turn pink, then it'll dissolve away, and at some point you'll put that drop, or that half a drop, or that quarter of a drop into the container that it turns that first stages of pink. That's what we want to see, that first changing. Well, here is, before I go there, let me just take a look here. Take a look at this. This is from the book, this chart right here. These are a list of some common acids and bases. Let me adjust this. So one of the strongest acids, the one we'll usually be using, is going to be hydrochloric acid. And then nitric acid, we won't use that. Apparently dentists use that. When they go to put a filling in, they'll put a little bit of nitric acid. This is what my dentist told me last Monday. They put a little bit of nitric acid on your teeth to slightly begin dissolving it so you get a nice rough surface for the amalgam of the filling material to go into. Anyway, each of these two have one hydrogen with them. Over here, sulfuric acid, H2SO4. We heard about that in the video about the volcano in Iceland, Katla, I think it was. Anyway, 2 hydrogens. So when this one disassociates, we got 2 hydrogens here. Phosphoric acid, H3PO4. Actually, it might have been phosphoric acid, I think. I think that's what the dentist was using. But this one, this would be called what they call triprotic. It's got 3 hydrogens, 3 hydrogen ions, 3 protons it can give up. Ethanoic acid, over here it's got this one over here it can give up. Actually, it might be this one of these over here. But anyway, when you look at these different acids, in our formulas, we're going to talk about how many hydrogens it has. And usually we're going to have acids that have 1 hydrogen. If we're using sulfuric acid, which we probably won't because it's kind of nasty stuff, it would have 2 hydrogens. So now you got to keep that in mind. So here we go. So here's our first calculation that we're going to do. Let me put this over here so we don't get too... So we've got the molarity of the acid times the volume of the acid that we've used times the number of hydrogen ions in the equation. That's going back. Usually for us it'll be hydrochloric acid, so there's 1 H in the acid. That will equal the moles of the hydrogen ion. And this should look fairly familiar to, we saw this more as molarity times liters equals moles. That's what we were working on before. And this time we're going to be multiplying it by this, and that'll give us the moles of hydrogen ion. Should be pretty familiar. Now, we'll get these, okay, I'd say pause right now if you could. Excuse me, not pause, hit the enter button, and we'll let them get that written down. Okay, now, for figuring out the moles of the hydroxide present, oh, sorry, that was cut off over there. That's moles of hydrogen up there. So, same thing for the base. You take the molarity of the base times the volume of the base times the number of hydroxides that are in the equation. Usually for us it's just going to be, there's going to be 1 hydroxide with what we're using, sodium hydroxide. And then so when you take the molarity times the volume times the number of hydroxides, that'll give us the moles of hydroxide ion in the solution. And if you need to pause that for a moment for them, you can. Okay, the next one here. So when we are doing the calculations after we've done the titrations, we're going to have this equation, okay? The molarity of the acid times the volume of the acid times the number of hydrogen ions, which is just going to be the moles of the hydrogens, are going to equal the molarity of the base times the volume of the base times the number of hydroxide ions. So here's what, okay, I'll let you go ahead and get that copied down, and then I'll talk about the implications of that. Let me zoom this in. you. All right. All right, now we're back. So here's how these titrations work. So we will be giving you a base that you know how much, we know the molarity of the base. You're going to know how much of the base you use, because with this burette right here, as you add chemicals in, like right here, maybe you start here at 20 milliliters, and then as you're doing the titration, you're adding it, and finally when it just begins to turn to pink right about at 28, okay, you subtract those two, and you're going to know the volume of the base. You know the molarity of the base. We know which base we're using. We're going to know the volume of the unknown acid we put in, because we're going to put in like 20 milliliters or 15 milliliters. We're going to know what type of acid it is. The only unknown we're going to have is going to be this. What is the molarity, the concentration? And with this equation now, and with getting laboratory data from using the burettes, you're going to be able to calculate how many moles of acid. And this is really important in chemistry, because a lot of times when they measure how much of something there is in a liquid sample, they're using some type of a titration. It's not always the simple one that we're doing. There'll be other ones, but it comes down to the same thing. They're using this equation right here. So let's do a practice problem now. So let's read through the problem before we start writing everything down, because you don't want, oh, excuse me. Now, let's read through the problem before you start writing it down. If it takes 35.7 milliliters of 1.25 molar sodium hydroxide to neutralize 25 milliliters of hydrochloric acid, what is the molarity of the acid? Okay, so first off, you need to know the balanced equation. And in this problem, I would say what we do is you can just put, let's see, we can put OH, because that's what our compound is. We've got 35.7 milliliters. Instead of writing this whole sentence down, we're just writing what's given. Just put down the given. And then we've got, so 35.7 milliliters of a 1.25 molar NaOH solution. Okay. And we want to neutralize 25 milliliters of HCl. Okay, and we're going to be looking for the molarity of the HCl. And we know the equation from what we just did before. So we got the givens put in. I guess the next thing we need to write is the balanced equation. We need to know that we've got one hydrogen in this reaction that's dissociating, and we've got one hydroxide. Okay, so it's a 1-to-1 ratio. That's why this is such a nice one to use. Sometimes you'll have an acid that'll have, say, 2 hydrogens it's giving up, and then you might have a base that's got 3 hydroxides, and you got to do molar ratios, but we're not doing that now. So the solution is to, pun intended. Okay, so let's write out this equation again. This might be a good time to hit the enter button. So again, like in any equation we've done our base equations. And when we come over to here, let's now substitute in. Oh, this is looking complicated, so maybe we can talk it down, make it a little bit easier. So what we got, we're looking for the molarity of the acid. So I'm just going to put a question mark above that. And let's see, we know that we used 25 milliliters of the acid. We know that there's 1 hydrogen ion in hydrochloric acid. The molarity of the base we know is 1.25 molar solution. We know from here that we used 35.7 milliliters of that. And we know from the equation here that we've got 1 hydroxide ion on there. So this really becomes 125 times 35.7 times 1. And then we got to divide that answer by, it looks like, 25. And that's going to tell us the new molarity of the acid. And from that we can calculate, okay, so we got it, yeah, there we go. If you need to pause, go ahead and hit the enter button. I got to quit saying it. Hit enter to hold this for a moment. Okay, we're going again. So let's see, 125 times 37 times the 1 divided by the 25 times 1. And hopefully you got that the molarity of the acid was a 1.7585 molar solution. And again, remember, molarity means that is it's moles per liter. And from that, if then we needed to find out exactly how much of the acid it was in there. A lot of times when we do these reactions in the real world, they might give you a sample of water and they want to find out how much magnesium or calcium is in the water, because we have heavy water here in Clovis and Fresno. So you could do a reaction like this. You react the calcium or the magnesium ions with an acid or a base, and then you can figure out in that sample of water how much of it's calcium. Then you can figure out parts per million or things like that. Let's see here. Yeah, there's another. Yeah, I think we'll stop right there for now on this. So next week, when I'm back, we're going to be beginning to do these calculations. Well, I'll give you unknowns. You'll calculate them. I think you can really enjoy it. It's really fun working with this stuff. When my first job I had in college as a part-time job was working in a laboratory, Twining Labs down in downtown Fresno, and one of my jobs was to titrate to find out, I think it was calcium and magnesium in water. Anyway, you don't care about that. Oh, wait now. Okay, hold on. I'm getting ahead of myself here. Let's see. You've got a worksheet to work on. Oh, let me find it here. Sorry, I forgot about that, but fortunately, I got it. No, okay. Wait just a second. Don't panic. I'm really talking more to myself. Here we go. Okay, so after this, your job, chemistry students, okay, you should have just seen the video on the proton. Yay. So on the back of that video, we've got this chart right here, and you should be partially familiar with this. I think you should know that pH is the opposite of the hydrogen ion concentration. And so looking at the chart, whatever your pH is, your pOH, when you add the two up, they're going to equal 14. Usually we use pH, but sometimes, I guess somewhere in chemistry, they're going to use pOH. So when we come down here, if we've got a pH of 2, in the water, the pOH, the hydroxide concentration, is going to be 12. And again, remember that in a reaction, you've got hydrogen ions. They're reacting with hydroxide ions, and they're in an equilibrium where this is basically happening like this. So they're going back and forth constantly, so you're going to have some hydroxide in the reaction and some hydrogen ion in the reactions. So when you look at this chart here, so pH of 1, pOH of 13, these have to add up to 14 always. They all add up to 14. When you come over here, if the pH is 4, that means you've got the decimal place has been displaced over 4, because these concentrations, this is a molar concentration over here, so the higher these numbers get, okay, the higher the pH number gets, the more basic it is, the less acidic. See, and this should make sense. There's less and less and less and less and less and less hydrogen ion concentration. Now when you go to fill in the chart down below, you just use the chart up here. I mean, like here, we got a pH of 7. So when you come up here to the pH of 7, okay, it's going to be there's going to be 1, 2, 3, 4, 5, 6 zeros, and then the 1, so you can get that filled in over there. That's going to make this 10 to the negative 7. That'll make this one over here. Now, with these, the minus 5 and the minus 9, they're always going to add up to negative 19. Excuse me, negative 14. So you want to work on that. You can add up the pH and the pOHs. They should always equal 14, and then whether it's an acid or a base. Then down here, I'm going to have you work on questions 1 through 8. And you know, you can, if you want, you can probably put these up here to show your work on that, because there's not enough room down there. But we've given the example there. We just want you calculate the pH and the pOH of each of these. And I mean, come on. You got a 0.01 molar solution of HCl, 0.01 molar, 0.01 molar, pH is 2. All right, goodbye everybody. Signing off.